Okay, so let's do this little practice right quick, guys. This is going to be where we try to balance your half reactions. Okay, so look at the rules over there on balancing half reactions. Rule number 1 is you want to determine what is the redox. What's the reduction? What's the oxidation? So I see an element here. So what would the element be? 0. This is another element, but this element actually has a charge. It means it was actually bonded to an anion, but during the net ionic, when you split them apart, we canceled out your spectator ions. And so this one actually has a charge of +1, a charge of +3, and then this right here, again, is just a plain old element that was never bonded to anything, so it has a charge of 0. All right, so aluminum, it went from 0 to a +3, and so it became more positive. So if it becomes more positive, how does that happen? You lose electrons. All right, so if I lose electrons, Leo, that was your oxidation. So your oxidation was actually where aluminum, the element, went to aluminum with a +3 charge. Okay, and now I have hydrogen. It went from +1 to 0, so it became more negative. The only way it can become more negative is to gain electrons. So gain electrons, reduced. So your reduction was going to be your hydrogen going from H to a H2. All right, so that was step number 1. Step number 2 says you want to balance all elements that are not hydrogen and oxygen. So if I look right here, I've got 1 and 1, it's good. 1 and 2. So what do I need to do to my hydrogen? Oh, and this was hydrogen with a plus. Sorry, I left that off. So I'm going to put a 2 right here, correct? So 2 hydrogens, 2 hydrogens. And really, I'm actually skipping that step because really I wanted to do first anything that was not hydrogen and oxygen. How do we balance out oxygens? You add water. How do you balance out hydrogens? Yeah, so really this would have been adding another H+. Well, H+ plus H+ gives me how many? 2. All right, so now I can balance out my charges. This charge is 0 and this is a +3. The only thing you can add are electrons. And so if this has a charge of 0, this has a charge of +3. If I add electrons, it's going to drop the charge. So which side needs to be dropped? This side does. So I'm going to add 3 electrons. So if I add 3 negatives, that will change it to 0. So now the balances are the charges are balanced. All right, so this has a charge of 0. This has a charge of +2. So how many electrons need to be added? 2 over here to the reactant side. All right, so now this is -2 + 2 gives me the 0. Okay, so now that I've got this right here done, now I want to be able to add them together, kind of like Hess's law. In order to add them together, though, my number of electrons have to be the same. So what does something 2 and 3 have in common? 6. So I'm going to multiply everything here by 3. So if I do that, it'll turn this into 6, turn this into 6, and it'll turn this into a 3. I'm going to multiply everything here by 2. So 2 aluminum, and 6 electrons. Okay, so now I can add them together kind of like your Hess's law. So we're going to cancel out anything that was the same on both sides of the reaction. So 6 electrons, 6 electrons. And so you have 2 aluminum elements plus 6 hydrogens is going to give you 2 aluminums with a +3 charge plus 3 hydrogen elements. And so that's how you would balance those half reactions.
I do a correction.
You can check to see if I finished grading yours or not. It's in that stack to the left of my desk. All right. I don't think I had another one on here that I really wanted to do. Let me just double check right quick. On your homework, we're going to do one of the problems though. Oh, I did want to do this. This is like the problem that you had on the back. So on this particular case, they've already pulled off the oxidation. They pulled off the reduction. Guys, look right here. What would this be classified as? Reduction or oxidation? They're showing it where I popped 2 electrons off of the copper. That would be your oxidation, losing electrons. So the copper that was an element, we popped 2 electrons off, and when we do, it turns it into an ion. This right here is showing where it's gaining an electron. So gain electron is your reduction. All right, so here, they've already balanced everything out with the charges. So they did steps 1 through 5 for you already. They've already balanced this one right here, the charge by adding 2 electrons. They balanced this charge by adding 1 electron. So now in order to add them up, what would I have to do? What would I have to do to be able to add these, like on the back side?
Multiply your silver by 2.
Multiply right here by 2, 2 and 2. That way I've got 2 electrons, those cancel out. So it'd be copper elemental plus 2 silver ions will give you copper with a +2 plus 2 silver with a 0 charge. All right, I want to do problem, let me see somebody's paper. 16A on the worksheet. It had Fe with a +2 charge plus MnO4 negative, and that's going to give you Fe plus 3 plus Mn plus 2. All right, so on this problem right here, you're going to have a quiz next time y'all come in here, and you're going to have to be able to do some of these. Now, whether I give it to you like this, where I've already done everything, you just now have to add them up, or if you have to start from the very scratch, where you have to start everything and balance out your half reactions. All right, so first things first, you can look at your charges. Guys, oxygen is not here. Really, it's just going to be iron and manganese. So I have iron that goes from a +2 charge to iron with a +3 charge. And then you have manganese that goes to Mn plus 2. All right, so, hey, what's happening here? It became more positive. How did that happen? It was oxidized. So this is your oxidation. This becomes, that would be your reduction. If I actually find the charge of your manganese right here, it's going to actually drop in charge some. Okay, so if I look at this, I want to balance out any elements that are not hydrogen, oxygen. Well, I've got one iron, one manganese, one manganese. I don't have to worry about that. So now let's worry about balancing out my oxygens. All right, so I've got oxygen here, but not on the right-hand side. So how do I add oxygen to the right-hand side? By adding water. How many waters do I need to add? I have 4 oxygens, so I need to have 4 oxygens over here, so I'm going to add 4 waters. But when I do that, the addition of water gives me hydrogen. So I need to add hydrogen on this side to finish balancing it. So how do I add hydrogen? 8H with a plus charge. Okay, so now all those elements are balanced. If I wanted to, we could check it. 8 hydrogen, 1 manganese, 4 oxygens, 4 oxygens. Okay, so let's balance out our charges. So this has a charge of +2, this has a charge of +3. So I need to drop this side down by 1. So what do? Add an electron. This gives me -1, so this would give me a charge of +2. These are now balanced. Okay, right here, I have 8 positives and I have 1 negative. It's going to give me 7. Okay, if I look here, this has a charge of 2 because that is 0. And so I need to drop this side down by how much? 5 electrons. So plus 5 electrons. Okay, so now I want to add these together. But what do I need to do in order to add these together?
Multiply the top by 5.
Yeah, if I've got 5 electrons and 1 electrons, I want to multiply everything here by 5. So 5 irons, 5 electrons. So now my electrons cancel out. Nothing else can cancel. If I had had water, and this is just an if I had had like 2 waters here on the left and and I had water on the right, they could have canceled each other out. So 2 of these would have canceled out 2 of these, leaving you with only 2 left. If I would have had, just like with Hess's law, if I would have had 2 waters right here, I would have added them up to make how many on the right? 6. But water was not in the top one. I just wanted to show y'all what it would do if it was. All right, so now I'm going to add everything to the left of the reaction together. So I have 8 hydrogens plus 5 Fe's plus MnO4 negative will give you 5 Fe plus manganese plus 4 waters. And that right there would be your answer. So this right here is showing the movement of those electrons, which is what redox is. Okay, let's move on. Oh, let me go pull up what y'all have to label today. Give me 1 second. Okay, so today y'all are going to be learning about electricity, like electrical charge. Okay, so y'all are going to be learning about how when we move these electrons, it creates some type of electrical current. Okay, so let's go to view, zoom, and I want to say I was 75%. Yeah. Okay, so guys, when we talk about redox, we're talking about the movement of these different electrons. And anytime we have the movement of those electrons, it produces some type of electrical current. Guys, we're not talking about electricity. Guys, guess what electricity is? It's just the movement of electrons. When I have lightning, guys, lightning, it has a lot of electricity in it. It is just the movement of electrons. That's why like your hair will start to stand up, or you get that like prickly feeling anytime like lightning's really close sometimes, because it's just ripping electrons off in order to form that lightning bolt. So electricity is just electrons. So if I have a movement of electrons from one atom to a different atom, we can actually measure some type of electrical current. And certain chemicals, when I put them together, are going to produce more of an electrical current than others. So in this particular case, I'm going to take two metals, and I'm going to put two metals together and create some type of circuit. And the amount of electricity coming off of that circuit depends on what two types of metals I am going to use. Some of these have a greater electrical current than others. All right, so in this particular case, this is what our battery setup is going to look like to try to create this electrical current. I gave y'all, or y'all should have picked up a second ago, this little handout. We're going to do two examples. We're going to do one on each side. And so you also need to have your reduction list. So this right here is a big table. If for some reason on a homework page I do not give you a reduction potential list, this is what you need to use. And so it looks kind of confusing because there's a whole lot of reductions going on right here. And guys, remember, reduction is where I gain electrons. So if you notice on all of these, they have an element plus electrons, and it gives you something solid because it's showing that element gaining the electrons. So this is the reduction table. All right, so this right here helps us to figure out what is that electrical charge going to be. And so for the very first one, let's just do copper and zinc. So copper and zinc. So these are two pieces of metal that I'm going to put in a solution. Guys, this is going to be some type of copper solution, and this is going to be some type of zinc solution. And so when we talk about these solutions, we want to make sure it's something that's going to easily break apart. So sometimes it'll be copper chloride, sometimes it might be copper nitrates, because if y'all remember back to solubility rules, guys, anything that was bonded to a nitrate ion is always 100% soluble. So I'm going to add some type of solution. In this particular case, let's add copper chloride solution. So if it's an aqueous solution, we know it's going to break apart into the cation ions and the anion. So for every one of these copper chlorides, how many chlorines am I going to have? 2. For every one of these compounds, how many coppers will I end up having? 1. And so if I uncrisscross it, there's a little 1 right there. So chlorine has a -1, copper has a +2. That means I'm going to put 1 copper with a +2 charge for every 2 chlorines. And they're going to be spread apart. I'm not going to put all coppers on the bottom and all chlorines on the top. They're going to be spread out because it's an aqueous solution and those molecules are moving all around in the water. Let's do another. All right, so I'm just showing that that piece of copper metal is sitting into some kind of copper chloride solution. And I'm going to do the same thing on the right-hand side. I'm going to put zinc in some type of solution, like a zinc chloride solution. So if I have zinc chloride, how many zincs would I have? 1. How many chlorines would I have? 2. What would the charge be on zinc? It's a transition mill, so you have to uncrisscross it to figure it out. So that would be a zinc with a +2 charge for every 2 chlorines. And another zinc with 2 chlorines. And another zinc with 2 chlorines. Okay, so I've got this zinc sitting in some type of zinc chloride. I've got copper sitting in some type of copper chloride. All right, off to the side, whenever you have one of these, and I'm going to tell you on AP tests, you'll have at least one of these, if not more. This is something they really like to ask, and it's an easy question. So anytime we see anything like this, I always tell the students, you want to write a couple of things off to the side, a couple of little anagrams. So I want you to write the word fat cat, and that means from anode to cathode. And it also has a double meaning. When I say fat cat, I also mean that the cathode is going to get larger. So the cathode increases in size. Okay, and then you need to remember anox. And I used to have a poster of these. I had a really big fat cat. I had an ox. And so there was a picture of an ox on it, and there was also a red cat. But I didn't put that poster up. I didn't want to have every single cabinet plastered with posters. Okay, an ox means that the oxidation happens on the anode. And red cat, that means the reduction occurs on cathode. Okay, so whenever we use these, you don't have to write the definitions, just write fat cat, anox, red cat. As long as you have those 3 things written down, then you can figure out this entire scenario. All right, and I did forget to add right here at the very beginning, you're going to have a voltmeter attached because I want to see, okay, what is this electrical current when I put these 2 things together and I connect all of my wires. Next week when y'all come in here after Easter, we're actually doing this lab. Y'all are going to take some of the metals, y'all are going to connect them together with some wires, and we're going to create this electrical current, and y'all are going to calculate how much electricity it should give off, and then you're going to go into lab and you're going to actually do this. It's really a really cool lab. This is something called a salt bridge. This is what is helping to connect everything together. Usually we use potassium nitrate because for one, potassium's in group 1, nitrates are always soluble, group 1s are always soluble. This will definitely break apart into the different cation and anion. What would it break apart into? What's the cation? Remember, I like cats. Cats are positive. So what would be the positive charge here for the cation? Potassium. So it'd break apart into potassium with a plus charge. And what would the anion? I hate ants. Ants are negative. So the anion has a negative charge. What would the negative charge be for this? Your nitrate ion, which is NO3 with a -1 charge. So in a second, we're gonna have to put down where those ions are gonna actually move. And I know this does not make a hill of beans just yet, but it will in just 1 second. I can't do anything else until I figure out which one of these is the anode and which one of these is the cathode. So that's when you're gonna take your reduction potential table right here, and I wanna find copper. Now look at the charge on copper. Copper has a +2 charge. That means it wants how many electrons to become satisfied, to fill that octet rule? How many more does it want to be happy again? Has a charge of +2. So how many electrons do you think it wants to gain? 2. So we're gonna find copper on this list that has a +2 charge. And so if I look at it, I'm gonna tell you where it's at because of time. It's not gonna be this one right here, because if you notice, this is copper with a +2, but how many electrons did it gain? 1. Instead, go up a little bit higher. Copper with a +2 charge plus 2 electrons gives you copper solid. that is the one that you want to write down. And I usually write it right here. I don't have a lot of space. Like I usually write it underneath these, but I'm gonna have to write it in between. So copper with a +2 charge that is aqueous is gonna gain 2 electrons to give you copper solid. Now this right here, I'm just gonna put E value. So that's the name of the column that I'm fixing to put. I want to know, what is that electrical charge gonna be? What is your voltage? So get a piece of paper, lay it on there, and tell me, what is that charge? It's a lot of little words, so make sure you're getting the right one. What is that voltage? What's that current? Huh? 0.34, a positive point.
All varsity baseball players at this time. All varsity baseball players. Are you ready for this?
Okay, so now we're also going to add in zinc. And if I flip it onto the back side, we can find zinc. Zinc has a +2 charge, so how many electrons does it want? Yeah. How many electrons does it want to gain? 2. So, hey Caleb, I will post this in just a little bit. If I
I'll
don't,
text you.
message me. Hey, have a great Easter. And do great today at the game. But hey, get rested up. Okay, what is the voltage for that one?
Negative 0.763.
-0.763 volts. Okay, so both of these are showing the reduction, showing where I'm gaining an electron. All right, and I don't want that. One of these has to be oxidized. So going off of these values, we're going to have to figure out which one is oxidized, which one is reduced. Guys, you want to look at the more positive number. Even if they're both negatives, you try to find the more positive number. Which one would that be? Copper. It has the more positive number. And so this right here is going to stay as your reduction. Because if you look at the title on that page, it was the reduction table. And so the more positive one, we're going to keep as the reduction. All right, so that means that this right here has to be the one that's being oxidized. So this one's going to gain the 2 electrons from the zinc, who is going to lose 2 electrons. So I want to flip this where I show that it's going to lose 2 electrons. And so...
Wait, is the more positive one is the reduction?
Because this right here is labeled as the reduction table. And so you're going to find which one of these has the more positive value, because that's going to stay as the one we call reduction. And so if that's reduced, then this one has to be the oxidized. And so if I flip this, I'm going to rewrite this as the reactant, these as the products, and what's going to happen to that E value? It's going to be the same number, but it's going to change to positive. So I'm just going to go ahead and take that negative sign off. Sometimes I'll put a line through it and write it underneath it, but because of my limited space, I'm not going to do that. So I'm going to say zinc solid is going to lose 2 electrons to become zinc aqueous plus 2 electrons. So that is just written in reverse. And when I did that, I was able to flip the sign. So in order, now this becomes the oxidized. Because remember, Leo goes Ger. So lose electrons oxidized, gain electrons reduced. And so it's gaining electrons, so this is reduced. This lost electrons, so it is oxidized. All right, so now in order to figure out what is the electrical current going to be with these 2 solutions, now you can actually add them up. So with your calculator, add that up. Figure out what that voltage is going to be.
1.123. Because 3 is 0, and then 0.7 plus 0.3 is 1 plus 0.1.
So what did you say it was?
1.103.
1.103 volts. And so on this voltmeter, whenever I have everything connected and I have 2 electrons that are moving, I don't know if it's going to be in this direction yet, if it's going to be in this direction yet, my voltmeter would show 1.103 volts. That would be the electrical current that I am measuring. Okay, so now that I have this labeled as reduction and oxidation, now I can use those 2 phrases, an-ox. So the anode is going to be where the oxidation occurs. So what was oxidized? It was your zinc, right? So an-ox. So your anode is going to be the oxidation. So this right here is your anode because this is where oxidation is occurring. Okay, and then red cat. So reduction is going to be your cathode. So this right here would be the cathode because reduction is occurring here. And I'm adding a little bit more onto here than I have to. It's like I usually try AN and CAT. And I don't usually write some of the definitions off to the side. So this is the anode, this is the cathode. All right, so now that's when this phrase comes in at fat cat. So the electrons move from the anode to the cathode. So the electrons are gonna move in this direction. From the anode towards the cathode. Now, how many electrons are being moved off of here? 2 electrons. 2 electrons, 2 electrons, 2 electrons. All right, so where did those electrons come from? They came from the zinc. Now, I've got to figure out which zinc. Was it the zinc solid or was it the zinc solution? And if I look, where did those electrons come from? Came from the solid because the zinc with a +2 charge has already lost 2 electrons. And so as I rip electrons off of the zinc solid, it's going to turn into an aqueous zinc. And so zincs are going to start popping off of here because it's not an element. They're not going to be attracted to the solid zinc. They're going to come in here and assimilate into this liquid. And so if I start using some of the solid zinc and making these little zinc ions that are going to start floating around in the solution, and I'm going to have a buildup of zincs with a +2 charge, zincs with a +2 charge. What do you think is going to happen to the size of this? Because I'm using it up. What's going to happen to the size?
Decrease.
It's going to decrease in size. And this is really wrong to say this, but a student told me this once. They're like, hey, the anode, like anorexia. What happens whenever you have anorexia? You typically lose weight and you get smaller. And so anode, if you want to remember it that way, anode is going to get smaller. And it's because it's losing some of the zinc solid because it's turning into a zinc with a +2 charge. So now it's going to give those 2 electrons over to the wire, and now they're going to come down here. But this is already happy. It has this octet rule filled. Does it want any extra electrons? No, but what does? The copper with a +2 charge, because it gave up its electrons to the chlorine, so it's missing its electrons. So it says, hey, you don't want those electrons, but I do. And so now, as these electrons move through the solid piece of metal, that copper solid does not want them, but the copper that's in the solution does. It says, hey, I'll take those 2 electrons. And when it does, it's going to turn it into a solid piece of copper, like elemental copper. And so the elemental copper is going to be attracted to the solid piece of copper. And so they're going to plate onto here. So they're going to plate onto here. What's going to happen to the size of the copper? It's going to increase in size. And that's why we call this the fat cat. So not only does it talk about how the electrons move from the anode to the cathode, but it's also because the cathode gets larger in size. So it's kind of a double meaning there. All right, so to finish connecting everything, because remember with electricity, you have to complete your circuit. So we just showed, we ripped off 2 electrons. The electrons are going to go through the wire. I'm going to measure the amount of current through the voltmeter. They're going to come down into the copper metal. I'm just going to give the 2 electrons to the copper, but I still have to finish going this way, and that's where the salt bridge comes in at. All right, so.
Beth,
Yes, ma'am.
can you send Abby Bailey to sign out?
Yes, on our way.
Thanks.
Can you hold off for just 1 second? Because I'm almost
No, I'm
done.
okay.
All right, so look, if the copper with the positive charge is coming over here, what kind of charges are going to be left over? Negative charges, right? So I'm getting rid of all of these because they're attaching on. So what's going to be left over? negative charges in here. So the positive part of this solution is going to be attracted. You're going to have a whole bunch of K's over here. And then look, I had a whole lot of positives being added to this solution. So if this has a lot more positives than negatives, what part of the salt bridge is going to be attracted? I've got more positives here than negatives. So it's going to be the negatives. So these are going to be attracted over here. So this is going to allow the electricity to go, okay, negative, positive, negative, positive, negative. It's going to complete this circle. It's going to allow those electrons to still have this current moving all around. That is what I want you to see. And so really fast before you have to leave, for tonight's homework, we're still going to do one more problem, and I'm going to erase this and we're going to do the next problem. But on tonight's homework, that's what you're doing. It shows a couple of different metals. I like this first one was aluminum and magnesium. So you're going to put aluminum and you're going to put magnesium right here and just assume it's aluminum chloride, magnesium chloride. It doesn't really matter. The next one's going to be zinc and iron. Oh, you know what? Let's actually omit number 3 on the homework. Omit number 3. And you might tell a couple of your friends because y'all are the last class to see this. So omit number 3 on the homework. But you're going to show the movement. So look for aluminum with a +3 charge. Look for magnesium, zinc, iron with a +3. Zinc with a +2. And then on the back, it's going to be pretty much the same exact way. Copper with a +2 and iron with a +2. Nickel with a +2, silver with a +1. Cobalt with a +3, silver with a +1. You're going to look to see what all is happening. You're going to draw a couple of these out. But that is what I want to see. I want to see the electronegativity values. Okay? So let's do one more. So let's clear, flip your page over. Let me clear my board, and we're going to do one more set.
I can wait.
Yeah. Huh?
I can wait.
Do you not have somebody waiting on you?
No, I drive. I'm good. Like, I can do one more. I'm good.
Oh, are you sure?
Yes, I'm sure.
Okay. All right, so I'm going to leave this right here up here. And this will go a little bit faster now that I'm not having to explain this as much. Okay, let's do iron and lead. Okay, so those are your metal pieces. Let's just say that I have iron chloride. So if I crisscross that, what does that tell me? Fe2, and then Cl's with a negative. So Fe +2, Cl's negative, Fe +2, Cl's negative. All right, and then we're gonna do PbCl2. So if I uncrisscross, it shows that Pb has a +2 charge, so it wants to gain 2 electrons. Okay, and let's go ahead and say salt bridge. And we know it's going to be some type of potassium. Oh, it's going to be potassium nitrate. I just don't know which direction to put potassiums and nitrates yet. And you're going to have a voltmeter. All right, so this right here is just the basis. And now, in order to finish solving for this, you have to actually look at your reduction tables. So now let's look at our reduction tables. So you have iron with a +2 charge. I believe it was on the back. And so it wants to gain 2 electrons. So it's going to be right here along the back. So if I have Fe +2 plus 2 electrons goes to Fe solid, what is that E value for it? What is that value? Okay, and now I want lead with a +2 charge. Remember, it is right here on the very bottom, the third equation from the bottom on the front side. What is that value?
Negative 0.125.
All right, so now that I have those written, one of those is the reduction, one of those is the oxidation. And you have to try to figure out which one is which. So I told you, you want to look at the more positive number. They're both negative, but which one's more positive? The lead. And so therefore, since that's the reduction table, this is going to be definitely the reduction. And I want to flip this to show the oxidation. So I'm just going to put a line through it. And I'm going to say Fe solid, breaking down to Fe plus 2 electrons. And that's going to give me a voltage of 0.440 volts. Now I can add those together. And I want you to tell me, what is that voltage difference? So add them together. 0.315. Now, if I notice, that's a lot lower than the other two metals, so it's not going to produce as much of an electrical current. And guys, we're talking about the electronegativity values. Which one of these is going to want those electrons more? So we talked about electronegativity last year. We talked about it already this year. What is the most electronegative element on that periodic table? Because remember, it's going to increase as you go to the top and to the right. What? Huh? No, not helium, because group 18 already has all their electrons. So do they want to gain any? No, they don't want to gain any more. So which one is it? Fluorine. So as you go to the top right, it's going to become more and more electronegative. Now, some of these are side by side on the periodic table, and so their electronegativity values are almost the same. And that's kind of what's going on with lead and zinc. Sorry, lead and iron. They're both meet transition metals. Lead is higher up, but iron is higher up, but lead is further to the right. They're going to have similar electronegativity values. So there's just going to be one that's going to be slightly more electronegative than the other. It's not going to create a lot of difference in their electrical charges. And so this voltmeter is going to measure 0.315 volts. All right, but now that I have this right here written out and I flip this, so I know that that's the oxidation, now I can say an ox. So an ox, what was oxidized? Iron. So now I know that this right here is the anode and red cat. So the reduction was the cathode. Reduction is your lead, so this right here is your cathode. Okay, and fat cat. It's going to go from the anode to the cathode. Bye. Have a good Easter. From the anode to the cathode. How many electrons? 2 electrons. Okay, so this is flipped versus what we had a second ago. And it's fine. It doesn't matter. They can go one way or they can go the other. That's why you have to figure out what is the anode, which one's the cathode. All right, so fat cat. What's the cathode going to do? Size-wise. It's going to increase in size. Why is it increasing in size? Let me move that chlorine over here.
Because the solid lead is gonna, or the solid.
Yeah, solid lead will stick to the.
Those 2 electrons are going to actually make this become solid lead, and it's going to stick to this. And it's going to make it get larger in size. All right, but where did those 2 electrons come from?
The anode.
And they came from the anode. What specifically?
Iron.
The iron itself. And so when those 2 electrons pop off of it, it's going to turn it into Fe plus 2, 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 Fe plus 2. So there might be a question saying, like an FRQ question that asks, describe the difference in mass of the iron before the reaction and after the reaction. Well, what happened to the size of the mass of the iron metal is going to decrease. And it might say, justify your reasoning. Why did it decrease in size?
Because the 2 electrons from the iron flow to the lead.
Right, you could say, but since it is the anode, it's going to give off 2 electrons, turning the iron solid into iron with a +2 charge, which will therefore go into solution. So it will decrease the mass of the iron solid. And there's a couple of ways that you can ask it. They always like to ask questions like this. Okay, so if you just stopped right there, they would not give you your points on the AP test, because what am I still forgetting to do?
Your potassium and nitrate.
The salt bridge. All right, so look at this. I'm gonna have a buildup of what over here? What came out of solution? The positives. So I'm gonna have a buildup of more positives than the negative charges. So if I have a buildup of all these positive charges, what part of the salt bridge is gonna be attracted? The negative, which is your NO3. And there are sometimes that people will use potassium chloride instead. So if I'm using KCl, what would be attracted over here? It'd be the negative charge, so it'd be the chlorine with a -1. You have to show that negative charge. So chlorine with a -1, but in this case, I'm using KNO3, so it'd be NO3s with a negative charge. And right here, since the positives are going away, now what do I have a buildup of? Just negative charges. So what part of the salt bridge is gonna be attracted right here? Potassiums. Just like that. And so they could ask for your, what is the E value? E is just talking about your voltage. What is that E value of this scenario, of this setup? And I believe that's something that y'all's homework is asking for.
Where's the NO3 coming from on that one?
Because you're taking, like when we do this lab next week, we're gonna take a piece of filter paper, like coffee filter, nothing special or fancy, and you're gonna let it sit in some potassium nitrate solution. And so then we're gonna end up taking, you know those well plates? You know, things with all the little circles right here. And you're gonna put a piece of like copper metal and, oh, I don't know, what did we do a while ago? So this would be like copper metal. And I'm gonna put it in a copper chloride solution. And then right here, I might put a piece of like zinc metal, and I'm gonna put it in a zinc fluoride solution. And so what you'll end up doing is taking that little piece of filter paper and you're going to connect those 2 welds. As long as the ends are sitting in the 2 holes, it's already soaking wet because of the potassium nitrate solution. And I'm gonna attach an electrode up to this, to a voltmeter. And I'm gonna attach it using little alligator clips. And you're gonna create your circuit. You're gonna create that current. And so then I can unattach it. Not over here, I might have the same thing, but I might have lead. And that way you can do a lot of small experiments at the same time. So you can do copper versus lead. And then you can do zinc versus lead. And I'm gonna have y'all do like 4 different ones to see, okay, calculate what do you think the charge should be, and then you're actually going to do it. So it's kind of a cool little lab. But yeah, no, it's just because we took that salt. Other people actually have a piece of glassware, but you have to pack it really tightly and with a stuffing material. It's gonna have ions in it, but the easiest way is to take just that little piece of filter paper and just let it sit in some potassium nitrate for a while. Just enough to create that current.
Well, you already have this, like the little strips soaked by the time we get in here, so we don't.
Oh yeah, and really all you have to do is let it, just get it wet. I mean, it doesn't really even have to soak. You just have to get it wet with solution. So it doesn't even have to soak. All right, so that's it for today.